All right, so here's our big first topic of chapter 7, which is the integration by parts formula, or just integration by parts. So I think the best thing to do is let's just start off by defining some things. So if h of x equals f of x times g of x, and we use the product rule. So let's say we want to go ahead and differentiate this using the product rule. All right, we get the derivative of h of x, which we know the product rule is f of x g of x plus g prime of x f of x. And if I misspoke, this is supposed to be f prime of x. I can't remember, and I'm not going to start this video over again. So this is the product rule. Now, what's really interesting about what we're going to be learning here is we know that there's a relationship between differentiation and integration. Just like U substitution and the chain rule are related to each other, they're inverse operations. Integration by parts and the product rule are also inverse relationships. So there is, like I said, there is the relationship between the product rule and integration by parts. That's the biggie right here. All right. So let's go ahead and let's try this. Let's see what happens. All right. So we're going to integrate h prime of x dx and integrate. Oh, this is going to be a biggie. You know what? I'm going to use a bracket because I'm going to have a lot of parentheses. So we're going to integrate g of x times f prime of x plus f of x times g prime of x dx. So we're going to integrate both sides of that product rule. Well, this is going to give us the following. We get h of x, which is defined as f of x times g of x, and that's going to equal the integral of g of x times f prime of x dx plus the integral of f of x times g prime of x dx. In other words, we're going to take this integration symbol and we're just going to distribute it. As long with the dx, we'll distribute that as well. All right, that's all I did there. Nothing fancy. And then I said on the left-hand side, the integral of h prime of x dx is nothing more than just the two functions that we originally multiplied using the product rule. Okay? Now, let's solve for the integral of f of x times g prime of x dx. All right, so we're going to solve this entire equation for this. So that's going to give us the following. And make sure you just follow along. You'll see it's not as bad as you think. It's going to be the integral of f of x times g prime of x dx, which equals f of x times g of x minus the integral of g of x times f prime of x dx. So let's get out some color and let's do this. First, right here are the same things. Next, here's f of x, g of x. And all I did is I took, we'll use this bright green. I took this term right here, the integral of g of x times f prime of x d of x, and I moved it from the right side of this equation to the left side by subtracting. So that's right here. And congratulations, we have just found the integration by parts formula. Now, to help us, we're going to make this look a lot nicer. All right? We're going to use the following substitutions. We're going to let u equal f of x, v equal g of x. And in turn, du is going to be f prime of x d of x. And dv is going to equal g prime of x dx. So this entire formula up above just turns into nothing more than just the integral of u dv, which is equal to u times v minus the integral of v du. And this is what you've probably seen. If you've seen this before, this is what you would have seen in every single calc book that exists. Okay? So let's go ahead and officially define this. All right? So we have our definition, integration by parts. We let u equal f of x and v equal g of x be functions with continuous derivatives. Then the integration by parts formula is the integral of u dv minus, the integral of u dv equals uv minus the integral of v du. All right, so this is something that you definitely want to write down on a nice separate sheet of paper, or maybe you want to put this on a note card so you can test yourself to recognize it when it pops up. So now let's go ahead and let's do some examples. Let's evaluate the integral of x e to the 2x dx with u equal to x and dv equal to e to the 2x dx. In fact, let me rewrite this. And dv equal e to the 2x dx. All right, now, whenever we do integration by parts, we're always going to create a little table. All right, and I'm going to give you some guidance on what we do with this table, but for now, just kind of follow along with me. Maybe don't even write anything down, just watch the example, pause the video, go back, write it down, and follow it again. But the table that we're always going to write is going to be this. So we have u, and then we're going to have du, and then we're going to have v, and then we're going to have dv. All right? Now, where did I get these from? I'm going to scroll up. It's right here. Everything's in this definition. Now, like I said, I'm going to show you later on at least some guidance on what goes where. But for now, I'm telling you, let u equal x and let dv equal e to the 2x dx. Now, in the first column, u equals x. Therefore, the derivative of x is going to be 1 times dx. So this over here should look very similar. That's like u substitution, all right? Now, on the right-hand side, right-hand side or the second column, we have dv equals e to the 2x dx. Well, how do we get back to v? Well, if you integrate the integral of dv, you get v. Therefore, we're going to have to integrate e to the 2x dx, which is going to give us 1/2 e to the 2x. So that is how I got this. And how did I get 1/2 e to the 2x? Well, I used u substitution. And if you need to, go back to my previous video where I go over how to integrate e to the u du. Okay? So now that I have all the information, I'm just going to go ahead and apply my integration by parts formula, which is very straightforward. So the integral I forgot the problem already. X e to the 2x dx is going to equal, now, integration by parts. uv x times 1/2 e to the 2x minus the integral of v du. So that's going to be 1/2 e to the 2x dx. So let me come underneath. This is u times v minus the integral of v times du. This is our integration by parts formula. So now I just have to integrate 1/2 e to the 2x dx again. So this is going to give me, let me clean this up. It's going to be 1/2 x e to the 2x minus 1/2 times the integral of e to the 2x dx, which is 1/2 x e to the 2x minus 1/2 times 1/2 e to the 2x plus c, which is 1/2 x e to the 2x minus 1/4 e to the 2x plus, we'll say k, where k is equal to 1/2 c, which, to be completely honest with you, you really don't have to worry about this little part. If you wanted to, you could have just rewrote this as c, again, because a constant times a constant is another constant. However, when you get into higher math courses, DiffyQ and stuff like that, sometimes you have to define what that is, all right? Because remember, whenever you integrate, you get a family of solutions. You don't get one solution. When you use an indefinite integral, you get a family of integration solutions, or integral solutions is what we call them. All right, pretty good example. Very straightforward. Now you can see how this integration by parts thing works. But I'm going to come back to this. I'm going to come back to this right here, because I kind of said, here, let u equal this and let dv equal this. But a natural question would be, well, how do we choose what we put and where do we put it? Okay, so we don't always do this, but we generally choose u and dv. There are exceptions, okay? And those exceptions you'll know when you hit them, because you can end up getting in a loop of integration by parts. Like, you could just keep doing it over and over and over and over again. And when that happens, you did something wrong. All right? And it's not that you did something wrong, it's just you got to tweak your technique a little bit. So we generally choose u and dv. So the acronym that we're going to be using here is LIATE. I've heard some students call it LIATE. I've heard others call it LIATE. I don't care. It does not matter to me. All right? What matters to me, though, is you know this. All right? And the acronym stands for the following. So L stands for logs. I stands for inverse trig functions. A stands for algebra. T stands for trig. And finally, E stands for exponential. And what these do is they help us to determine what is u and then dv. So logs are first, inverse trigonometric functions are second, third would be algebra, fourth would be trig, and finally e would be exponentials. And this is the process in which you let u equal first and then dv equal second. So this is first, dv is second. Now what really makes this, like, I guess kind of work is that you always want to make sure that this dv thing, you can properly integrate it. All right, that's really what this is all about. All right, and since we do not have integration formulas that allow us to do, or that allow us to integrate simple log functions and inverse trigonometric functions, it makes sense that we should not use them for dv. So you want to integrate the easy stuff, differentiate the more difficult stuff. But like I said, that doesn't always happen, okay? But this is like a, 95% of the time, this is what you're going to be doing. In fact, all of your homework is basically going to follow this trend. I may put one of them on there that doesn't follow this trend, okay? But you'll know it when you hit it, because you're going to sit there and go, oh my gosh, I have to integrate by parts again, and then I got to do it again, and then I got to do it again, and then I got to do it again. And it's like a never-ending while loop, okay? So let's look at an example where it's just straight up integrate. That's it. So, oops, I want a black marker. So let's evaluate the integral of the natural log of x over x to the third dx. Now, before you do anything, you always want to make sure that you rewrite this in a nice linear format. That way you can easily identify things. So here, just by looking at this, we have an ln, so we get a log, and then this is something you would see in algebra class, or an algebraic function. So if I'm using my acronym, I'm going to let u equal the natural log of x, dv equal x to the negative 3. So now I can easily find du. Actually, let me use a different color for that. So now I can find du very quickly, and I can find v very quickly. And that's what this is all about right here. This is a perfect example of what we're trying to do. All right. So when I integrate x to the negative 3 times the natural log of dx, we're going to use integration by parts. U equals the natural log of x. Therefore, du is going to be 1 over x dx. And v is just going to be the integral of x to the negative 3. Sorry, I forgot to write the dx there. My bad. So we're going to integrate x to the negative 3 dx. And when you integrate that, you end up getting negative 1/2 x to the negative 2. And now, using our formula, uv minus the integral of v du, we end up getting u times v. So let's see here, that's going to be the natural log of x times negative 1/2 x to the negative 2 minus the integral of v, negative 1/2 x to the negative 2 times du, which is 1 over x dx. Okay? So there's a lot of algebra here, so we just got to be careful with this, all right? This is going to give us negative 1/2 x to the negative 2 times the natural log of x, just cleaning this up, plus the integral. And let's put the 1/2 out front, because a negative and a negative make it positive. So that's how I got the plus 1/2. Pull the 1/2 out front. And then x to the negative 2 times 1 over x is just really x to the negative 3 dx. And now when I go ahead and integrate, I get negative 1/2 x to the negative 2 times the natural log of x minus 1/4 x to the negative 2 plus c. And just to kind of clean this up a little bit more, it's going to be negative 1 over 2x to the second times the natural log of x minus 1 over 4 x to the second plus a constant. And there's your answer right there. Okay, now the next two examples are really going to pinpoint some stuff. The first one is going to be where we have to use integration by parts more than once. So let me write this down. Next two examples are special cases. All right, so here's the first example. Integration by parts more than once. All right, so we have the integral of x to the second e to the 3x dx. All right, so once again, we approach this like we would any other problem. All right, we're gonna use Lie8 to help us determine what is going to be u and then dv. So algebra, exponentials. So since a comes before e in Lie8, we're going to let x to the second equal u, and then dv is going to equal e to the 3x dx, which means du is going to be 2x dx. All right, and remember, I will divide both sides by 2, so 1/2 du equals x dx. And then when I go to integrate e to the 3x dx, I get 1/3 e to the 3x. Now I'm going to go ahead and substitute everything in, and I'm just going to make it look real nice right from the start. So uv minus the integral of v du. So u times v is x to the second times 1/3 x to the 3x. However, I'm going to write 1/3 out front. Then I'm going to put x to the second e to the 3x. All right? Minus the integral. Now this is going to be v, which is 1/3 e to the 3x. So let's put the 1/3 out front. So this is going to be v. And then we're going to multiply this by x dx, or I'm sorry, du. So that's x dx. So that's going to be x dx. But since it's 1/2 du, I'm going to make this 2/3 by multiplying this by 2 again. So I guess I really didn't have to do that initially, which is fine by me, I guess. All right, so you end up with just 1/3 x to the second e to the 3x minus 2/3 times the integral of x e to the 3x dx. Okay, now when you go to integrate this again, all right, notice this is a product rule, x times e to the 3x. So you're going to have to do integration by parts again. All right, we have no other options about this. So we're going to go ahead and do this, and you'll see just how large, I guess, these problems can get here. So the whole process repeats. U is going to equal x. dv is going to equal e to the 3x dx. So du now equals dx. And then when I integrate this, we get v equals 1/3 e to the 3x again. All right, so the only tough part here, all right, is to remember where things go and what you have before. So we have 1/3 x to the second e to the 3x minus 2/3. All right, so let me color code this for us. Let me go ahead and get a nice color here. So that's all this right here. That's going to be all this right here. All right, times, and I'm going to exaggerate this here a little bit, times Now, we need to do integration by parts formula again, but for x e to the 3x dx. So it's going to be uv, so x, and then v is 1/3 e to the 3x. So I'm going to put a 1/3 out front, e to the 3x, minus the integral, all right, of, let's see, what is that, v? So that's going to be 1/3 out front, e to the 3x, du is dx. Whew. All right. So getting this out, this right here is my second integration by parts. All right, so this is the second integration by parts. All right. So going from left to right, 1/3 x to the second e to the 3x minus 2/3 times 1/3 x e to the 3x minus, now we have 1/3 times e to the 3x. Its integration is 1/3 e to the 3x plus c. And now algebra time. So 1/3 x to the second e to the 3x minus 2/9 x e to the 3x minus 2, oh, that's not 2/9. That's going to be 1/3 times 1/3 is 1/9 times 2/3. Oh, I think it's 2/27 e to the 3x plus c. All right. And here is the problem, all right? This is a fully online course. So WebAssign is going to expect you to simplify this. So make sure you take your time with the algebra. No rush, all right? And if I were you, I would just try some things, all right? And what I mean by try some things is maybe, just maybe, when you get to this part right here, where I just put that star, maybe type that in the WebAssign and see if it says yes. And if it says no, then you're going to have to go ahead and simplify all the way down, all right? So my role of advice, my opinion, just a suggestion, be careful with algebra. All right? Because the majority of the time, when I'm helping students out with calculus, it's not really the calculus that I'm helping them with. It's the algebra. So please, please, please be very careful with this, okay? Now, the next example is our second special case. And in this case, this is where Lie-8 actually fails us, okay? So if we wanted to integrate t to the third times e to the t to the second dt. So very similar problem to what we just did. I mean, it's extremely similar, all right? But watch how this fails, all right? So if we just take Lie-8 for granted, let's just say, okay, this is what it is, and it works 100% of the time. Watch what ends up happening. T to the third, well, that's definitely algebra. E to the 2t, I'm sorry, e to the t, e to the t to the second power. So how about I just say e to the t squared? All right, it's definitely an exponential function, right? And if we took this for what it is, that means u would be t to the third, and dv would be e t to the second. And then du would give us 3t to the second dt. However, when you go to integrate e to the t to the second dt, you can't do it. There's no way to do that. We do not have a technique other than numerical analysis in which we can integrate this. And what I mean by numerical analysis, What I mean is you literally type this into a computer and then you tell the computer, add up 5,000 rectangles, and you got to program all this stuff in there, and you get an approximation to what this is. You never get an actual exact answer. You can't do it. So this is where Lie8 actually fails us. So we got to be careful. So maybe let's switch it up a little bit, okay? Let's switch this up a little bit. So let's try choosing some other stuff. In other words, let's go ahead and let's try u equals t to the second. Therefore, du is going to equal 2t dt. Now, if this is the case, then v has to equal t e to the 2t, no, I'm sorry, e to the t to the second. Oh, I wrote this in the wrong spot. I'm sorry. dv is t e to the t to the second dt. And when we integrate this, we end up getting 1/2 e to the t to the second by using u substitution. So here's what I did. That t to the third, I just separated it as t times t to the second and rewrote it like this. And the reason is because I said, well, maybe if I let this equal u, I also have it right there, so I can go ahead and rewrite some stuff. All right. And honestly, this just comes with practice. This isn't something that it's like, oh, you can instantly see it. All right. Just gotta be you just gotta be careful with this. So, using our formula for integration by parts, let's write that v a little bit nicer. uv minus the integral of v du. All right. The integral of t to the third e t to the second dt is going to equal u minus v. So let's see, u is t to the second, v, okay, so we get 1/2 t to the second e t to the second minus, and then it's going to be v, but v is 1/2 e t to the second, so I'm going to pull the 1/2 out front, times the integral of e t to the second times du. Now, I'm going to pull that 2 out front, so this is going to be not 1/2 anymore, but it's really 2/2 t dt. And that 2/2 right here, oh yeah, you're right, that simplifies down into just 1. So there it is right there. And now, when we integrate this, we get 1/2 t to the second e t to the second minus the integral of t e t to the second dt is equal to 1/2 e t to the second plus c using u substitution. And that's going to be it for this video. So I hope this really helped, and see you in the next one.